Hello everybody and welcome to this week's video in which we will be looking at, shocker, we've done question 1, we've done question 2, we've done question 3, we will be looking at question 4 from chapter 10 of Jackson's Classical Electrodynamics first edition, which is to do with alpha waves of some arbitrary amplitude. That's arbitrary amplitude. Yeah, alright. Slightly shorter problem, so this hopefully won't take that long. I'm a bit naughty. I'm recording this video on Monday, so I'm sorry that it's come out later than they usually do. Went to bed last night very late and thought, oh dear, I haven't recorded the video for tomorrow. And I was busy all of this morning, so it doesn't matter. It will come out by 8 PM instead of 8 AM. That's alright. Anyway, let's get started. So, what does the question ask? Well, 10.4. An incompressible, non-viscous, perfectly conducting fluid with constant density ρ0 is acted upon by gravitational potential psi and a uniform static magnetic induction B0. Show that magnetohydrodynamic waves of arbitrary amplitude and form B1, which is a function of x and t, and v, which is a function of x and t, can exist and are described by these three equations, which are b0 dot del times b1 is equal to plus or minus root 4 pi ρ0 times db1 dt. The second relation is that b1 then equals plus or minus root 4 pi ρ0 v, and p plus ρ0 psi is equal to b0 plus b1 all squared over 8 pi, which is plus b1. Try that again. P plus ρ0 psi plus b0 plus b1 squared over 8 pi is a constant. It says it on the thing. I don't think it matters that much how I read it and if I make mistakes. Anyway, we'll just sub these relations, or we'll sub things into other things, namely the magnetohydrodynamic equations. So momentum equation first, we have that ρ0 del v dt plus, why do I keep saying del? ρ0 v dot del, that is del v, don't forget the arrows, is equal to minus del p plus minus even ρ0 del psi plus 1 over 4 pi curl of b cross b. We have an identity over here, so that's just this, minus a half, del b squared, put that in brackets, may as well. We can rewrite the right hand side, I'll just do RHS, is equal to minus del p plus ρ0 plus squared over 8 pi. Oh, we're looking pretty good, aren't we? Plus 1 over 4 pi v0. I didn't forget to do a thing on top, this is deliberate. v1 plus 1 over 4 pi b1 that should be a cross there, running out of space. That's alright. We have something very useful here, which is in the question we are told, let me get out, no, I will stick to only white pen, we can pretend we're on a blackboard. Anyway, we are told in the question that it is incompressible non-viscous perfectly conductive fluid with a constant density, which means that a couple of terms here go to 0, namely the gradient term. Yeah. So That's nice. Bye-bye. Let's do left-hand side. Left-hand side. Yeah. Equals, rather. So we can sub that v is plus or minus b1 over 4 pi rho, and we can sub that in. I think we can get away with that here. Yeah. So it should be plus or minus square root of rho naught over 4 pi t plus 1 over 4 pi b1 dot del b1. Nice. Which means we can make things cancel. Because those two are on both sides. So that will cancel out. And then we are left with the final equation that's... also, I forgot something. Oh, we can do things with the 1 over 4 pi and bring that to the other side and put that under the bracket, I think. Maybe. Because otherwise we won't end up with the right thing. Let me see. Yeah, no, that checks out. If we multiply both sides by 4 pi here, then that will go to the top in that bracket. So plus or minus root of 4 pi rho naught b1 dt is b naught b naught. Nice. Okay, that's one of them. We have done number 1. The next one we can do by the induction equation, I think. Or even we can, no, we get the same one by the induction equation, and then we can sub things back into it. Yeah, because if they both reduce to this form, and we subbed in those two equations, then we must be right. All of them must be right. Yeah, I remember this. So, b1 t is del cross v cross b, which is del cross v cross naught plus del cross v cross b1. That's induction. Since v and b are parallel, v and b1 even are parallel, that's just 0. And del cross, that's also 0. So we're just left with that bit. Sorry for scrubbing over it, I didn't mean to do that. That's better. Oh yeah, and then we can just identity that. Also, note that del dot v is 0, del dot b naught is 0, b naught equals constant. Actually, that just simplifies straight down to b naught. There, okay, nice. Yeah, and then we can just sub in the same thing as before. Therefore, because v is b1 over, so then you just throw that to the other side. In fact, I may as well write it out nicely so that it's obvious. Take that to the other side. Plus or minus square root of 4 pi rho naught is equal to b naught del times b1. Cool, and since that and that are the same thing, we didn't do any approximations. Yeah. So they can exist, because we just came up with the maths for them. I think that's allowed. If you come up with the maths for something, does it work? See, that I wouldn't agree with that, but I'm as in not this. I agree with this, obviously, but the notion that if something is mathematically possible in physics is possible, because you could do physics with mass being negative and it might still work out. And in fact, you probably would see some quite nice symmetries in various places, but banned because mass can't be negative unless something funky is going on, like when you calculate the plane at the end of the test and it's taking off at minus 499 henries per meter squared. Such an old meme. Right, let's move on. That was part A. What is part B got to say? Oh yeah, I should read it out, shouldn't I? Right, so B says, suppose that at t equals 0, a certain disturbance B1 x naught exists in the fluid such that it satisfies all the above equations with the upper sign. What is the behaviour of the disturbance at later times? We can do a differential equationing here, I think. So at t equals 0, we're going to have... That was not a del. I tried, but it wasn't. A D, a partial. A partial is what they're called. I meant minus. Cool. I'm going to throw in alpha and velocity here. VA as B naught over root 4 pi rho naught. Yeah, plus or minus. I don't care for plus or minus. Not that deep. That's an engineer's problem. Standard linear advection equation, possibly. B1. That's what it says in my notes, and I think it's not very hard to get there, is it? Yeah. And we have a general solution for this for B1. Yeah, xt. It should be x, not x. It should be that x. I'll do that. No, it's not bold. Yeah, no. I don't think it's bold. No, is it? I hate this stupid font. It doesn't make sense for it to be. Good. Oh my goodness, is that possibly... is that possibly Suvat? Is that possibly Suvat? Also... So... fx equals b1 x 0. Yeah, we can actually... I think we can get physical interpretation out of this. Basically, we'll have a rigid body with velocity minus the output velocity. It would be non-dispersive, and it will propagate parallel to magnetic field lines, so opposite direction to P0. There'll be no change in form or damping or distortion over time because it's just linear input. Okay. But yeah, that was really short. Oh my goodness, 15 minutes. Some of these questions are easy. Maybe I'm slacking off because I'm... As in, none of these questions are easy. Some of these questions are less impossible than the other questions. I keep notes of 2 questions at a time. I'm going to go and do the next 2 questions after this. And the first one was a bit more things going on. But yeah, nice. I hope you enjoyed. I hope you found this interesting. Go and try the next problems, and then my answers will be out next week. Thank you very much, and I'll see you then. Bye bye.